Welcome back. In the last episode, we introduced METARs and went over the basics: station identifiers, wind data, and visibility. Now, let's dive deeper into some of the more specific components of METARs that pilots use to make informed flight decisions. Let's start with precipitation types. METARs often include information about weather conditions like rain, snow, fog, and hail. Understanding this data is crucial for pilots when approaching airports, especially in low visibility conditions or during storm systems. For example, SHRA means light rain showers, while TSRA indicates thunderstorms with rain. These abbreviations help pilots quickly understand the intensity of weather at the airport, which aids in planning approaches and diverting if needed. Also, pay attention to recent weather indicators in METARs. This information will tell you if the conditions have changed significantly from the previous report. A report might say recent SHRA or recent TS, meaning the weather has shifted to rain or thunderstorms within the last few minutes, which could affect your landing. Another important aspect of METARs is the visibility information. Visibility is reported in either meters or statute miles, depending on the country. For example, 10 sm in the US means the visibility is 10 statute miles. It's crucial for pilots to understand visibility, especially when considering approaches to airports with limited lighting or foggy conditions. When visibility is reported as RVR, runway visual range, this indicates how far a pilot can see along the runway. RVR is typically used for low visibility conditions and helps determine whether instrument landing system (ILS) approaches are required. RVR readings help ensure that pilots can see the runway to safely land. Let's talk about cloud cover. METARs describe cloud height and coverage using abbreviations like FEW, SCT, BKN, and OVC. These terms describe the amount of cloud cover present at various altitudes above ground level. For example, BKN 080 means broken clouds at 8,000 feet, while SCT 030 means scattered clouds at 3,000 feet. Pilots use this information to assess whether cloud bases are high enough for a VFR, visual flight rules, approach, or if they need to prepare for an IFR, instrument flight rules, approach. Cloud cover also indicates the potential for turbulence. Cumulonimbus clouds, CBS, which produce thunderstorms, are dangerous for pilots. When METARs report CBS in the area, pilots will adjust their altitude to avoid severe turbulence and thunderstorm activity. Another key piece of data is temperature and dew point. These two values are crucial for understanding the potential for icing, especially during descent and approach. The dew point indicates the point at which the air becomes saturated, and if the temperature drops below the dew point, there's a risk of cloud formation or fog. For example, if the temperature is 0 degrees Celsius and the dew point is also 0 degrees Celsius, there's a high chance of freezing conditions, especially when flying at higher altitudes. Pilots need to monitor this to decide when to use anti-icing systems on the aircraft. Let's focus on altimeter settings. The METAR reports the QNH or altimeter pressure setting, which pilots use to set their altimeter to ensure accurate altitude readings. If the QNH is too high or low, the aircraft's altitude could be inaccurate, leading to potential safety risks. For example, Q1010 means the sea level pressure is 1010 HPA. If a pilot is flying into an area with low pressure, they might find that the actual altitude is higher than the altimeter indicates, so adjustments need to be made accordingly. Next, let's look at special METAR reports, also known as SPECI. These reports are issued when weather conditions change significantly and need to be updated between regular METAR updates. For instance, if the visibility suddenly drops or thunderstorms develop, a special METAR is issued to provide the most up-to-date information. SPECI reports are crucial during rapidly changing conditions, such as passing squall lines, severe storms, or strong wind shifts. Pilots must stay alert for these updates, especially when flying through dynamic weather conditions. Another important piece of information is wind gusts. The METAR reports not only the steady wind speed but also the peak wind gusts. These gusts are significant because they affect takeoff and landing performance, especially on runways that are aligned with crosswinds or near turbulence-producing terrain. Wind gusts are reported with the G abbreviation. For example, 28015 G30 kT means the wind is coming from 280 degrees at 15 knots, with gusts up to 30 knots. Pilots must be prepared for sudden changes in wind direction and speed, particularly near mountains or thunderstorms. Let's discuss runway conditions. METARs can sometimes include information about runway surface conditions, such as wet, icy, or snow-covered. This information is important when planning landing approaches in areas that have frequent rain, snow, or freezing conditions. Runway condition reports often indicate whether de-icing is needed or if slippery conditions might affect landing distance. In winter conditions, some METARs include the braking action report, which describes how well the aircraft can decelerate on the runway. Pilots adjust their approach and landing speeds based on this information. Let's move to real-time usage of METARs. Pilots use METARs to determine the best approach method, whether it's ILS or visual. When the weather is poor, METARs guide pilots on when to use instruments and whether the weather meets the approach minimums. For example, if the cloud base is low and visibility is restricted, pilots will likely opt for an instrument landing system (ILS) approach. METARs provide the necessary information on whether localizer and glide slope signals are available and whether the airport is within approach criteria. Let's finish with how METARs are used for flight planning. Before taking off, pilots review METARs for departure conditions. If weather conditions are poor, especially near the departure airport, they can assess alternate airports in case a diversion is needed. For long-haul flights, METARs are also used to monitor weather changes along the route, particularly near fronts, low-pressure areas, or monsoon regions. Pilots will adjust their flight path to avoid weather systems as necessary. In the next episode, we'll continue exploring METARs with Part 2, focusing on how they are used in flight planning, approaches, and alternate airport selection. We'll also discuss how TAF reports complement METARs for complete weather forecasting. See you in Meteorology number 52, METARs, Meteorological Terminal Forecast, Part 3.